Thanks so much, and I am really appreciative, especially of the fact that this is all in person. It's so exciting to talk actual physics. It's much more stimulating that way, and I hope that I can tell things that are appropriately provocative to you, that we will also have an interesting and more interactive discussion here. So yes, quantum black holes. Black holes, quantum black holes are interesting. It's a theoretical laboratory, if we might say so, for quantum gravity. There are many different interesting features. There's breakdown of relativity at the singularity. There's an event horizon that has at least some non-local features. The quantum nature is quite concrete, so our progress on quantum information has been interesting. And the black hole entropy enumerates how many quantum constituents that the black hole has. So it gives us a lot of information about what the black hole is made out of. So there are many different directions here that black holes have been useful for. There are many areas that have been very active, and especially active recently. There's been progress on precision entropy for supersymmetric black holes in ADS space. We've identified the actual microstates in quantum field theory. It's a new direction that I've been quite a bit active in. There's been a much better understanding in the last few years of the flow of quantum information, so the quantum implementations of ADS-CFT holography. I know there's been quite a bit of activity here on that, but I have not been so active in that area. And then there's been discussion of near extremal limit of black holes. There's been progress on that. The SI-Cray model has been particularly prominent, and also its relatives. So what I'll do within all this set of many different directions is that I'll just have to pick and choose, and I'll especially discuss just the near extremal limit of black holes, where I'll say things that will sound very, very familiar, but I will say them in ways that are different from the way most people will say it, and those of you who have studied this before might very well find your rotten tomatoes and eggs or whatever else you throw with and start making complaints, because I will probably also say some things that are heretical. I will discuss just a simplified setting, because I know that it's inevitably a broad audience. So I will just discuss 4D Einstein-Maxwell theory. It means black holes have quantum numbers that are the mass, the angular momentum, and the charge. These are the Kerr-Newman black holes, and they are in the textbooks. It's a standard setting. Their entropy, computed from the area, is given by some formula that is a little bit complicated, but not exceptionally so. So it has a little bit of structure. One of the key features of this formula, and the only thing actually that I need it for, is that I want to point out that there is a square root. That means that if the mass is not sufficiently big, that square root goes negative, and therefore it becomes imaginary. And this singularity is in fact real. If the mass is not sufficiently big, and by sufficiently big, I mean precisely this big, the square root goes negative, and the area becomes imaginary, and there really are no black holes that have mass below this. This is called the extremal limit. It's the lowest possible mass for a given charge and angular momentum. And we see it from that formula. Now, in my kind of strategy and the way that many pursue, we kind of are interested in black holes that are not necessarily extremal, just like that, but that are supersymmetric. What's the difference? Well, that's one of the things that I want to explain. Well, of course, for one thing, I told you that I want to be interested in Einstein-Maxwell theory, because you would know it from textbooks. Well, secretly, that is, in fact, the bosonic part of n equal 2 minimal supergravity, so I can pretend that my Einstein-Maxwell theory is, in fact, a supersymmetric theory. So I can ask, in the supersymmetry algebra of that theory, that is the extended with fermions, Einstein-Maxwell version, what is the unitarity bound? What does the supersymmetry algebra look like, and what do I get as a BPS bound? A BPS bound for that theory is this. M minus Q has to be positive, but that means that we see immediately that the extremal bound, I said, was the lowest possible mass you could get for a given Q and J, is just not enough. If you want supersymmetry, you must also have M equal to Q. And if we look at the extremal bound, that means we must have J equal to 0. So the saturation of this bound, a supersymmetric black hole satisfies two conditions, not one. It's not enough to be extremal. It must also satisfy a different condition. And for these very simple black holes, the Einstein-Maxwell theory Kerr-Newman black holes, the second condition is J equal to 0, zero angular momentum. In these other contexts that I also do research on, like ADS black holes or so, the constraint, this second condition, is vastly more complicated. There are many charges, and they all appear, and it's very nonlinear and all that, and not that illuminating. You should just say, J equals 0. It doesn't look like a fantastically complicated equation, but it is an equation. It sets a constraint on the quantum numbers. Namely, one of them have to be 0. So there are two quantum numbers, J and Q, that I can use to parameterize my set of black holes in. Each of them have a range of masses, but only if one of the quantum numbers is equal to 0 can I have supersymmetry. Oops. Now there's a corollary of this, that if you're interested in nearly supersymmetric black holes, then you can go away from the supersymmetric limit in two different directions. If for a given charge and angular momentum, you say, well, let me not go all the way down to the extremal mass. Let me have a little bit more energy than the minimal possible energy for that Q comma J. That's called adding temperature, having a little bit extra energy above the minimum possible energy. But there's also the, couldn't I add a little bit of rotation? Because my supersymmetric black hole did have to be non-rotating. And therefore, if I want to go a little bit away from the supersymmetric limit, I could add a little bit of rotation. The mass above and beyond the extremal limit, the BPS limit, the supersymmetric limit, is m equal to q, plus some quadratic terms in temperature and in rotational velocity. The coefficient there in front, the q cubed, is essentially the specific heat. The specific heat is in fact linear in temperature, so it's really the specific heat divided by temperature that sits in front here, and it's some 2 pi's, whatever. But this coefficient here, I'm going to loosely just call the specific heat. And the interesting part of this formula, there are multiple interesting things. One, as I've emphasized, there are two terms because there are two ways to go away from the supersymmetric limit. And these two ways have the same coefficient. The cost of making the black hole rotate a little bit is exactly the same as adding a little bit of temperature in suitable 2 pi kind of units. And the other point is that the new scale, this scale that sits in front here, the q cubed, well, I put the Newton constant to 1 by now. And this scale here in front is actually much, much larger than the horizon size. And this thing there is exactly the wrong way. Just making sure to keep you awake. Q cubed is much, much bigger than Q, when Q is a large number. So the scale is very, very large. That's interesting. It means that the low energy dynamics of this theory here, just above the supersymmetric limit, is dominated by very long wavelength dynamics, which corresponds to a very low energy above the minimal energy. So now, how do I want to analyze this situation? By now, I just gave you a little bit of phenomenology. What's the entropy? What do I learn from it? I learned a few things. How do I want to analyze it? Well, there are a lot of symmetries that must be kept in mind. There's superconformal symmetry. The ground state has superconformal symmetry. The supersymmetric ground state has that. There's a scaling symmetry in particular. The conformal part of the superconformal is a scaling symmetry and is broken. Is broken by the temperature if you go a little bit away. So it's a broken scaling symmetry. There's also an R symmetry. I actually have n equal 2 supergravity here. So I have 2 supercharges. I could rotate them relative to each other. And that is also broken. It's broken by the rotation. So we can think about the two parameters, the temperature and the rotation, as being parameters of broken scaling invariance and broken R symmetry. Then, of course, there's the big symmetry, the gravity. Gravity has coordinate transformations as its basic symmetry, diffeomorphisms. So the theme that I want to pursue and want to use to analyze the system is that I want to use my symmetry, and I don't want to use too much else. So I'm just going to think about this as effective quantum field theory. I'm not going to write down Lagrangians or some such thing. In fact, I'm going to say I don't really care what the Lagrangian is. I'm just going to use my symmetries and see what I can learn. Well, we start with our near horizon geometry. There, the metric is not so complicated. I don't want to run down these long, big formulas for metrics. Even the Kerr-Newman metric is quite long and complicated. This one is not. It's the near horizon geometry. It has constant negative temperature. I've written it in a form here in complex coordinates, c and z bar, but it's just a two-dimensional space. Think about it as the r, t plane that's very near the black hole. It is actually ADS2. It's also known as the Poincare upper half plane, and it has many other names, but it's a constant negative curvature space in 2 dimensions. Where is the black hole? Well, the z equal to 0, the origin of this metric, is what you should think about as the horizon. It's a Euclidean signature. The horizon is at the origin. Then from z equal to 0 out to z equal to 1, there's a throat. That's the approach to the horizon. Then at z equal to 1, that's kind of where the black hole ends. Because after all, this was the near horizon geometry, and that means that somewhere it ends, and there's a transition to the stuff that is not near. That's the thing that's kind of the surrounding space. So z equal to 1, this stuff here obviously blows up. But what is happening there, and the reason it blows up, is that the rest of the geometry matters. If you're inside, it does not matter. So simple geometry. Now, how can I learn about this metric, this geometry, just by using my symmetries? In fact, using my coordinate transformations. Well, symmetry determines the space of Brown states. And our basic symmetry diffeomorphisms means that we can rewrite the geometry in new coordinates. Now, that's not actually an interesting symmetry. Rewriting the metric in new coordinates, well, we identify a metric written in one way in one coordinate system with the metric that is the same actual geometry but written in other coordinates. Rewriting in the same coordinates does not change the geometry even though it looks different. The only technicality is that when I consider various possible changes in the geometry, then only normalizable changes should apply. If I were to change my basic background metric that I wrote down in a non-normalizable way, I'm going to cry foul and say, no good. Only consider changes in the geometry that are normalizable. And then among those, you're going to say, now identify these what looks like deformations, identify them if in fact they aren't real deformations. Identify them with one another if those deformations are just coordinate changes. It just looked like you changed the geometry, but you really just changed the coordinate system. But in so doing, you should only identify geometries that correspond to being related by a normalizable coordinate transformation. Non-normalizable coordinate transformations don't matter. They are not actual symmetries. So what are the normalizable deformations of the geometry? Well, they're really simple. They correspond to my basic metric that had just a diagonal ZZ bar piece that blew up. Well, if the ZZ piece is being changed, and being changed by just being some polynomial form, if you turn that into actually a general holomorphic polynomial, that corresponds to an interesting change of the metric. And we can ask ourselves, that particular change of the metric, is it a diffeomorphism? What would it mean if it is a diffeomorphism? It would mean that this metric, that this change here could be written as some nabla of a vector field. That vector field would be the direction of coordinate change that we need. And can it be written in this way? Yes, it can. I can, in fact, find a way of doing this by finding a diffeomorphism. This particular diffeomorphism is not very pretty, but this particular diffeomorphism is such that I get precisely this story. I should mention that this funny numbers here that I don't have the 0, 1, and, oh, well, 3 are missing anyway, so that there are three missing symmetries, and they're actually the -1, 0, and 1. They correspond to some geometrical symmetries. I'm not going to write them down, but these are the isometries of isometries of the ADS2, and they play an important role, but it's not actually the ones I'm after. The ones I'm after is that I change the metric. I only consider normalizable changes in the metric. They look like this. And then I say, are these things actually due to diffeomorphisms? They are. They're due to these diffeomorphisms. However, these particular diffeomorphisms are not normalizable. In fact, you can see that very easily. My metric clearly blew up near 1. That means 1 is dangerous. And in particular, it is no good when something is constant near 1. It means that when I compute the norm, it's going to go bad. Therefore, this diffeomorphism is not normalizable, but this metric change is. Therefore, we actually have distinct ADS2s. When we add some extra piece that exactly takes this form, it's just holomorphic, it has just a single function here, this kind of change of the ADS2, this is still actually ADS2. Why do I know? Because I have this non-normalizable diffeomorphism that actually is just a change of coordinates that just gives me this, and therefore I know that of course I can't change the curvature by just changing coordinates. Nevertheless, this coordinate change is not an allowable one, so therefore I must consider each of these guys a distinct geometry. My space of ADS2s is this space. And this H can be any regular function. It has to be regular, as in, has to be, it cannot blow up at z equal to 0, but it can be any then polynomial. And these deformations of the 2D metric that are not due to diffeomorphisms in string theory literature would be called quadratic holomorphic differentials. There are changes of the metric that are purely holomorphic. These things have been discussed a lot in string theory, where people just talk a lot about the 2D to 2D world sheets, of course, in that context, time and space along the string. And in that context, the moduli space of two-dimensional geometries with genus G is called the Teichmüller space. And what we have here is a very close relative. It's actually, at some level, a much simpler relative. This is what is called the universal Teichmüller space, kind of the union of all possible genus. So we can think about string theory as being a sum over compact two-dimensional surfaces, like spheres and tori and larger spaces with holes in them, but some that do not have infinitely large volume, that are just finite size. My ADS2 space is different because at z equal to 1, it blows up. It has infinite volume. So it makes it non-compact. The non-compact one is kind of like the genus going to infinity surface. Is the one that has infinitely many deformations. The normal Teichmüller space of 2D geometries with genus G has just a finite number, 3G minus 3 dimensions. But this one here has infinite dimensions because I have an arbitrary polynomial. But nevertheless, even though infinitely large geometries of spaces here are a little bit scary and a little bit unfamiliar, it's very simple. It's just a polynomial. So given that, how do I now go about using my quantum field theory knowledge? Well, the physical diffeomorphisms, they generate a symmetry algebra. What is the symmetry algebra? Well, I had actually my generators of these particular diffeomorphisms. I can go and figure out how they commute with one another, and I can see that they form an algebra, because of course two different diffs that take these polynomials to a different polynomial, well, if you take two of them and combine them, it takes it to yet another polynomial. So this clearly makes some kind of group. That group, I can go and look at my group table. What is it? It is the diff S1 group, as in the symmetry group that takes the circle to itself, but modulo an SL2. That's SL2 is my isometry. So whether or not you follow those words, don't worry. All I'm saying is that if you want all the ground states of this particular system, take a particular reference ground state you like. That could be the one I wrote down originally, which had no polynomial on, but that's only if you prefer that one. Then act with any element of this coset here. You're going to get a new geometry. Think about that as in you're going to change the polynomial to something else. But it didn't matter which one we decided was the reference one and which one we decide is the one that follows after you acted with a symmetry. This is a completely symmetric space, so I shouldn't take any of them as preferred. I should just say take any one of them. And then the space of group actions is the space of my ground states. These SL2s do not give distinct ground states because they're isometries, but all the others do. All my polynomials correspond to distinct ground states. And we should think about these ground states as degenerate. Historically, people said, it's really bad with ADS2, you can't do normal ADS-CFT correspondence because it gets boring. All the states have zero energy, and there are proofs to that effect, and people didn't like it. In the modern incarnation, I'd say, that's great. I have degenerate ground states. I have a lot of them. I have a lot of zero energy states, and I can write them down fairly concretely for you. It's just a polynomial's worth of zero energy states. That's what's called degenerate ground states. A large degeneracy. What do I do? And there's a large degeneracy that is generated by a coset model. That's the sort of thing we do when we do effective field theory. We say, I have a lot of ground states. What do I do with them? Well, the excited states, the low-lying excited states, they correspond to moving slowly among all the ground states. So if I take slowly moving excitations along all these ground states, that is actually my quantum space of deformed geometries that now have a little bit more energy. They're not ground states, but only a little bit because I can move as slowly as needed. So the space of slowly moving motions in this set of polynomials is the space of my ground states. This is called nonlinear realization of symmetry, and it's not exactly a new method. It's very standard. The only slightly new thing is that here there are infinitely many generators, and that's of course less familiar. It's much more familiar to have, say, an SU2 mod U1 or some such thing as your basic space of vacua. Here I have an infinite set of vacua, but that doesn't mean that I can't use just the standard formulae for writing down what is this set of energies I get when I write down a nonlinear sigma model on my space of geometries. And what I get is this action is the Schwarzian effective theory. Those of you who have studied the area would know to say, oh yeah, I know that. I've seen it before. It has something to do with the SYK model, or perhaps you say that it has something to do with the JT gravity model. And I will say, what are you talking about? JT gravity had some kind of dilaton or some such thing. I had absolutely no dilaton. I had the space of ADS2s. And then as you move on the space of ADS2s, you get this as the effective action for the low energy excitations. No dilaton, at least yet. Or if you had SYK, I'm going to say, no. You had a very complicated model that at low energy became this. That's the whole point of effective quantum field theory. You realize your symmetries with no prejudice about exactly what happened at much higher energy. You can certainly call it, yes. I mean, but notice, this is different. You're here, now you say, yes, it's like time parameterizations of the boundary. You can certainly think about it that way, but that was not how I thought about it. In fact, what I think I say exactly next is that there are two distinct perspectives on this. I took the perspective that this was quantum gravity in 2 dimensions. This was deformations of the metric, deformations of the geometry near the black hole. Or you could, as is being proposed, think about this as symmetry acting on the boundary and say, oh, there's a nearly scale invariant theory on the boundary that lives on the circle and it has no gravity. Well, guess what? This is kind of like a proof of holography in this simplified setting. This is a proof of the near ADS2, near CFT1 holography. And for that, it's very important that I took the perspective that I take that is from the gravity side as well as the one that is the boundary side. Not just the boundary side that perhaps I could use from my SYK model, or I could use it from some low energy geometrical point of view, but I've gone out of my way not using that point of view because I wanted to prove that there really are 2 distinct perspectives. One of them has to do with the space of possible metrics in 2 dimensions, Another has to do with the deformations of the circle at infinity. And those two, yes, is the same space. And therefore, they're equivalent. And therefore, we have the same effective field theory. And therefore, since they have the same effective field theory, we have two descriptions of the same thing, holography for you, at the level of effective field theory. Maybe that's a good time to ask questions. No tomatoes yet? Okay, that's very good, but you didn't get your dilettante. Well, there is, of course, this coefficient in front of my nonlinear action. That coefficient, the symmetry breaking scale, this is Ct over T, the Q cubed, is undetermined. In my phenomenology of my black hole, I took my area law, my mass formula, I expanded them and figured out what it was. But that was by actually having solved the Einstein equations and knowing actual explicit black holes and so on. Once I just analyzed the symmetries of my near horizon region, I don't have the slightest idea what this is. It's just a number that appears. From the low energy effective field theory point of view, this is just a number. It's the one we often would call f pi. If this was a pion theory or some such thing, it's just a number, and you should measure it. It's part of the input in your low energy effective field theory. But if it were to be that you actually knew the UV completion of this, then you would be able to compute it from that UV completion, such as the SYK model. Or perhaps you were partial to JT gravity or some such thing. In other words, you had a particular benchmark model of 2D gravity that you like. Then you could interpret this parameter in terms of that benchmark model and then say, that's how I give it names. And that would be then this issue of the circle. And this point of view would sort of say, well, look, I have my disk, and then the metric blows up at c equal to 1. Why don't I regulate that and go a little bit inside the disk and have a little circle in there, or perhaps a wobbly circle? And this you can certainly do, and that's what people normally do in JT gravity. I have a different point of view. I've insisted that I do analyze this space all the way out to z equal to 1. Please don't regulate it. If you regulated it, then my entire determination of whether something was normalizable or not will completely change. It was very important that the metric blew up at z equal to 1. If you don't blow it up, then your whole notion of what is normalizable and non-normalizable have changed, and you need a totally new discussion. I'm not ready for that. I insist that you go all the way out to z equal to 1. But then I am open to the idea that, well, what happens beyond z equal to 1? Oh, right. That's where the metric was different, wasn't it? It is no longer the near horizon. There's something else. This is what in effective field theory we would call matching with the UV theory. It exists exactly at the z equal to 1 point. It is the point where we go between the upper cutoff on my low energy theory, and we think about that as a fairly low energy of my UV theory. That, of course, is unknown. It's an unknown theory at the UV. But it is there I get my one piece of data that determines my low energy coupling, my f pi, or my, in this case.
Before 1 to 3, 0, 1, you're not really like quantizing so far. It's just a short and classical. So you have differential
Have I quantized it? I have not quantized it, that's correct.
Just the cutoff, then of course it's a finite dimensional system at this time.
Right. I have not quantized it, that's right. I could and I won't, but that's right. I could and I would do the same that many, look, once it's the same algebra, quantizing it is the same that everybody's doing. I get a vacuum character, so I'm not going to show much of this because I really frankly don't have much to add. What I have to add is I have a different perspective here. And this was the one that, it was not JT gravity, it was effective field theory, run-of-the-mill coset construction. And then how do I find now this scale? Well, let's recall our near horizon geometry. This was the near horizon geometry, the benchmark. Yes, I had some deformations. Scale invariance of this thing says that there's an overall scale here. It's actually Q for our extremal Reister-Nordstrom black hole, the supersymmetric ground state. What happens at z equal to 1? Well, that's what the throat attaches to the surrounding geometry. Z bigger than 1, it's where the not near horizon geometry is there. The way we should think about that is that from the point of view of the black hole, we have a sphere. The sphere at the horizon is something. If you go further out, the sphere gets a little bit bigger. How fast does the sphere get bigger? Well, if we go slightly further away from this extremal black hole, we'll say, oh, there the temperature is no longer 0. We are away from the black hole horizon. So there, if we have a rocket with sufficiently much acceleration, we can in fact avoid coming in. So therefore, we can avoid falling in as long as we have sufficient acceleration away from the black hole. And since we can do that, we actually have a particular finite temperature. Similarly, at that spot a little bit further out, the area is a little bit bigger. We can take the ratio of those two things. And the ratio of two things has a beautiful name. It's called taking the derivative. That's how we take the ratio of small changes. Oops. Oh, this was out of... I definitely put these at the wrong spot. That was bad. I have somehow put them in wrong order. Now we'll see if I manage to resort them mentally. Well, at any rate, the entire geometry for the extremal black hole, for the supersymmetric black hole, not just the ADS2 region, is of this form. This g of r is some particular function that you can look up. If that function is approximated in the near horizon region, it's actually just a 1 over r squared function. But if you go a little bit away, it is not a 1 over r squared function. So now how do you find the deformations away from extremality? Well, the specific heat is basically the change in entropy as you change the temperature a little bit. How do you change the entropy? Well, you change the area by a little bit. And how do I change the temperature? Well, the temperature is just the derivative of this function here. So I change the derivative a little bit. How do you change the derivative a little bit? You take the second derivative. Once you take the second derivative and then take the particular function for g, this is what gives me my coefficient. So I'm saying that there's an element geometrical way of thinking about my matching with the UV theory in the context of a black hole. I need the near horizon geometry, and I need one piece of data about beyond. Don't go and try to take the fully non-extremal black hole and Kaluza-Klein reduce and understand its dynamics. Take only the supersymmetric black hole. And that supersymmetric black hole, don't look at all of it. Look at one piece of data beyond the near horizon region, the derivative. The only piece of data you need for your effective field theory. That's your UV matching. Your UV matching is, do keep track of that second derivative, please. But that's the only piece of data that you will need. So this is the near extremal data from the extremal geometry. Yes? There's a question, no?
Oh, yeah.
So this is what I call the natractor mechanism, the near attractor. It's not the attractor. The attractor would be at the horizon. It's the near attractor. It's the derivative at the attractor, which actually takes you just beyond, but only in the sense of high school calculus. You went a little bit further. So what the near attractor mechanism does is that it takes the approach to the ADS2 attractor geometry. This is what's usually called the ADS2 attractor. This is the natural generalizations of it, is take derivatives further away. And this is really, really handy if you have a very complicated black hole, I can assure you. Don't have to solve Einstein's equations, don't have to analyze black holes, just take a derivative. Yeah?
Yeah, can you remind me if it is the usual finite size?
Yeah.
Black hole, Q and M is finite.
Yes?
And supersymmetric.
Yes?
BPM. And then this degeneracy of Bekenstein-Open entropy is exactly degeneracy, and you have mass gap at the microscopic level that people study this.
Yes?
So what is Q cube? Is that like, what's the relative size of Q cube and the gap? Q cube is pretty.
It is, no, it is actually, it's pretty much the gap. It's pretty much the gap. Well, gap is 1 over this.
Yeah.
Maybe half times 1 divided by this or something like that. That's right. So this is the gap. This is the gap. Right. But again, the gap, how would you actually compute the gap? Usually people say, oh, it's gamma or something. Oh, well, that was how you set the units. I'm saying in my actual black hole, because I look at very complicated black holes that have ADS space around and 5 different charges and whatnot, now go find out what this is. Oh, I'm delighted that all I need to do is to read off a metric coefficient in my solution, in my supersymmetric solution, which was much easier to find, and take the derivative of that coefficient. It's all I need to define my low energy theory. Don't need to go and do KK reductions and all that, which is what many, many people do. But I'd say
Schwartzian is really representing, because momentum is quantized, so that's this guy. Because the energy is quantized. Just to put it on a finite sample, S1. Z equal not exactly 1, slightly regularized.
yeah, I think I will take that in a second. I'll take that in a second for why is this thing also quantized? Yes, it is, but we can see that in a second. Here. So, see, here I only paid attention to the gravitational modes. But we also had a charge fields around. This was Einstein-Maxwell theory. So we do have a gauge field around as well. And we should really play the same game with that. We should ask, are there by any chance normalizable deformations of the gauge field that cannot be gotten from a normalizable gauge function? Well, these kind of normalizable AZs that are just polynomials, those, as it turned out, are actually normalizable. They're normalizable because when you take the square of these, then since this is a vector field, you must contract with the metric with upstairs indices, so you get a pretty big damping out towards your boundary where the metric blows up. Therefore, this whole thing is normalizable. And you ask yourself, can I write it as a pure gauge? Well, yeah, I can certainly find a sigma such that the derivative of sigma is equal to this. That would be called doing a high school level integral. However, you will determine that whatever this function sigma then is that you have just found, it is non-normalizable because it does not have a z index. So therefore, you don't get the opportunity to contract with a metric with upstairs indices that would give me damping enough, so that would give me a non-normalizable gauge function. Therefore, these gauge fields are in fact they are in fact physical. They look like pure gauge, but they are not. The effective theory of this thing here, along with my gravitational mode, just adds what in fact is a free gauge field. What is nice is that here, the relative coefficient, the fact that I just have a single overall coefficient, follows from the fact that this is an effective theory of n equal 2 supersymmetry. So spontaneously broken n equal 2 supersymmetry says that because the two are actually sitting in the same algebra, even though this algebra is not actually realized, or well, it's more precisely nonlinearly realized, but because of that, supersymmetry is strong enough that it can relate my two breaking coefficients. The fact that the temperature that extended things a little bit and the rotation that created the energy a little bit, they cost equally much. Supersymmetry is enough to explain that, even though it was just for Einstein-Maxwell black holes, in principle without supersymmetry. Even if I didn't know about supersymmetry, I could use it as a technical tool in intermediate states to say, that's really weird that these two coefficients were the same. Well, this is why they're the same. They had to be the same. Because I can supersymmetrize the theory, and that broken supersymmetry is broken in the near horizon region, and its breaking pattern says that these two coefficients is related by a single f pi, by a single low energy effective action number. Now, yeah, questions on the breaking scales. So now, more controversial things. So there's been a lot of discussion here on ensembles versus states. And I have a perspective on it, so I'm changing track now. The discussion that there's been in the literature and on Zoom, not much in person, unfortunately, has been on whether ADS-CFT is in fact described by states or by ensembles. Normally what we say in the black hole context is that ADS-CFT, well, we have a black hole, a single microstate of that black hole would correspond to a single state in the boundary CFT. And then there should be many possible states in the boundary CFT that correspond to all the different possible microstates. That's why we have entropy. So we have a given black hole quantum number, and we should figure out what are all the CFT states that are consistent with that quantum number, or those quantum numbers. Well, the recent discussion has found that sometimes it appears that a single black hole is in fact related to many boundary conformal field theories. This is confusing. The context where this has primarily come up is that one black hole can be described as an average of many matrix models. So these are matrix model black holes. They're not quite the black holes that I'm talking about. But in that context, the question has come up. Should we use ensembles, or should we of theories, or should we just describe black holes as states in a single theory? Well, in my line of business, where we've actually done a lot of precision studies of black hole entropy, basically understanding the entropy using the dual field theories, we have some perspectives on this. One of the things that come up in that kind of story when we try to do things with precision is that people often do not consider the partition function, as in fact they should in their microscopic theory. They consider the index. Why? Well, the index has this extra -1 to the f inserted, and that justifies extrapolation from weak coupling, think free theory, to strong coupling, think impossibly strong. And that is where the black hole, in fact, should be thought about as dual to the strongly coupled field theory. But the index, happily, is independent of that whole parameter, so it's nice in that way. However, it is not what you wanted to compute. In fact, there are a lot of states that cancel in this index. Apparently, somehow those extra states are unimportant. You might say, maybe there just aren't so many of them. Or maybe there just aren't that many cancellations. That's not true. In CFT examples, CFT2, in CFT2, we have right movers and left movers. The chiral primaries, these are the supersymmetric ground states, are such that the energy is equal to their spin. And the spin, because of the 2D Virasoro algebra, super Virasoro algebra, can have only a certain set of j's. It has to be from 0 up to what is 2k. K is the level of the dual SU2 level. Don't need to know what this is. All you need to know is that you have energies of the left movers, and you have the angular momentum of those left movers, and the energy and the angular momentum have to be the same. Kind of makes sense that that's supersymmetric. It's kind of like the left moving energy equal to the momentum. When energy is equal to the momentum, you're kind of moving at the speed of light. So you're in a shorter representation. That is what corresponds to supersymmetric state. And then, yes, you move at the speed of light. Energy has to be equal to the momentum. However, the energy and the momentum is not by itself determined. It can have many different possible values. Only the equality between the two is determined by the fact that we want a short representation, that we want a special algebraic property. No restriction on the right movers. This is the construction from what is called the elliptic genus in CFT2. You have left movers in some supersymmetric state, right movers in any state. The index then is insensitive to which state did you take here. Among the left movers, you should take a supersymmetric state, and then any right moving state. Which left moving state should you take? Whichever. So in a certain sense, I'm going to average over all of these guys in the index. Happily, my -1 to the f is such that even though I average over all these different guys, I count them collectively as one state. So when we're asking, are there cancellations? Yeah, there are a lot of cancellations. We end up taking all these different quantum numbers and simply not paying attention to which chiral primary are you talking about. We only ask, how many states are there among the right movers? Left movers, don't worry about them. The partition function does something different. If you were to think, maybe the index and the partition function were just somehow coincidentally the same. No, it's not the same at all. It actually takes them all into account. But it does something else. It does what partition functions do in StatMech. They take the average. So instead of saying, let's count them all as one, let's count them as if they all were the average. Everybody's average. But this is where the black holes have a magic that actually allows these two things to still look as if they're the same procedure. Why? Well, remember that the supersymmetric black holes, in this case in ADS3, have two conditions. One condition, energy has to be equal to momentum. Second condition, the momentum cannot be any momentum. It has to be a special value of the momentum. And which special value? The middle one. So the way I think about the black hole is that the black hole, the actual space-time black hole, can only have one possible value of J. The corresponding microstates, there are lots of different possible states. The black hole is by itself an average of all of these states. It's the only possibility that we have to get the parameters to agree is that the parameter that kind of the index was insensitive to, it just happens that the black hole actually averaged over it. It did not end up depending on it. If it had depended on it, our index strategy would have failed. But it happens that it does not, because supersymmetry has two conditions, not one. So let me make a less elaborate analogy. These formulae in ADS3, I didn't explain with great detail. If I go to higher dimensional ADS, they are much more elaborate. Yes?
Before you go, can you just go one slide back? I just want to make sure I understand. You're saying that not all of the states that correspond to the parameters in CFT2 actually are dual to the supersymmetric black hole because they have JL not equal to KL, most of those states?
All of these states are fair game. In my partition function, I should take any state that is in a left-moving supersymmetric state, and that's supersymmetric, and any supersymmetric or not among right movers. Any state would be fair game on the micro side.
Well, I don't know what you mean by fair game, but if I put the CFT2 state, if I choose the CFT2 state to be one that has JL not equal to KL,
Yeah.
what is the bulk dual?
It doesn't have one.
Good.
Gravity can only be, well, you might say that it's a singular bulk dual, or something like that. Yeah. It's when the square root has gone negative.
So then it's fair to say that only the states of JL equals KL actually have a gravitational bulk dual that's uncontrollable.
Sure, but I have these other states. And these other states, I would say, that is the entire ensemble of states that's dual to the black hole. The black hole is, statistical. I'm not the first one who says this. Everybody says the black holes are kind of statistical, and they're statistical specifically in the sense that they're averages over this parameter.
Well, I'm trying to reconcile those two statements, because on the one hand, you're saying that the states of JL not equal to KL don't have a gravity dual or a singular one. But on the other hand, you seem to be saying that you do want to include all of those states in what you call the boundary dual to the
I do.
black hole.
And then I take the average of them, and you get the middle when you take the average. There are exactly equally many that are above JL equal to KL and below. So therefore, the average of all these states, the ensemble average, is precisely JL equal to KL.
I think I'm asking a question which is which has to go both ways, right? I can either ask, what is the collection of CFT2 states that do have a good bulk dual, which is the supersymmetric black hole? And I think you would answer it's those states that have JL equal to KL. And I can conversely ask, what are all the possible boundary states that might be dual if I give you a supersymmetric black hole? And I think you would again say it's those states. I don't know why we would then discuss other states in the context of discussing such a black hole as well. That's the part that I'm all missing.
I think because we are not specifying this quantum number. I mean, like the index doesn't specify it at all. We're just saying, we are just counting how many supersymmetric states do we have.
I think you're just choosing to do something different. But I think the answer to the question we can ask lots of different questions. I'm trying to connect this other question that you would like to ask to the one that I guess I was asking, which is
But there are numerous ones of those as well. There are as many. There's still a classical number of them. So these other, it would be very strange if they were not, it's very strange in a way that they're not dual to black holes, because there's a large number of them. There's a semi-classically large number of them. You can compute a predicted area that you would expect your black hole to have. Then it's true you go and find that, wow, there are no such black hole. It's true. The way I interpret that is that what the black hole has done is that it has averaged over that quantum number. That, and that's, remember, we do necessarily, black holes necessarily have this extra supersymmetry condition. I think about that as averaging over the index direction, and that average over the index direction, alternatively, I can think about it as just a standard average. And that's how this constraint comes about. I need to account for the constraint somehow. And the way I interpret it is that supersymmetry does not prevent us going from one chiral primary to another. There's a chiral ring. A chiral primary and another one, they can add up and become yet another chiral primary, or they can split up and become a different one, become two chiral primaries. So therefore, it's very reasonable to think that these ones are forming themselves an equilibrium. That any of these chiral primaries is not like there's some special ones with JL equal to KL. Those can split apart, or they can meet some of the others. So therefore, it's entirely reasonable to think that we have an ensemble of such chiral primaries. They just kind of split apart as they please. This is why the index doesn't like them, because they can split apart, they could depend on the coupling. I don't like that. Therefore, I don't want to count them. I'm saying, don't worry about it. This is how we do things in StatMech all the time. We don't actually need to count the details. Just take the average.
So you're saying, I think, that if I consider Fourier superposition of all of these states, including the ones with KL not equal to
Yes.
KL, I can, well, it'll have, on average, it'll have KL equals KL.
Yes?
And you want to say, actually, that's the correct dual to, if I give you a supersymmetric black hole in the ball, I should think of the dual as being actually this mixed state.
Yes.
It could be typical state, I think.
It could be typical state,
Because,
yes.
This is a way to get the property of typical states. You can do that somehow. So in a high-dimensional, non-external black hole case, the way black hole entropy appears is different, because this E is a continuous parameter, and then you can get in any small window of E, you can have independent black hole. It's a density. But here, I think you have exact degeneracy, right?
Yes.
So the supersymmetry.
Well, they're not degeneracy, really, right? I mean, E equal to P. Then when you add up two energies, well, you have more energy. I mean, that's not degeneracy. That I don't know. Now, each of these chiral primaries are completely different.
But are you saying that for standard understanding in supersymmetric black hole,
Yes?
and the BPS separated,
Mm-hmm.
otherwise it doesn't, right?
Yes?
In BPS saturated, this ground state degeneracy, against the working entropy, is the exact ground state degeneracy, and you have a gap, Q.
I didn't say that.
Right.
You did,
So
and it's
you have
correct.
this. And this thing must be all physical because you can count
Yes.
that in radiation.
I think they all must be physical, and therefore this is why I'm saying that I can't that I think that this is not the correct interpretation, is because it could split apart. How I'm going to prevent it?
But, then I'm saying that
That sounds clear.
any typical state in this space spanned by these independent integrating step of galaxies have to be like black hole. Otherwise, statistical mechanics won't
Yes.
see this. So all these typical things must be black hole,
Yes.
and not just an ensemble. Ensemble is a way to get the property which is common to all these typical states. That's
Fair enough.
Yeah,
I
that's
think
what
it's typical versus ensemble. Yeah. Let's discuss a little bit more after. I will just finish the thought here with more provocation. So yes, they are much more different. Now, the way I think about why is this relevant for the discussion of the ensemble average? Well, in these ADS black holes, there are many more concrete situations. But let me try instead, because I want to be just in the basic Kerr-Newman kind of situation that I wanted to use as a pedagogical example. Well, there we have in mind that there's a distinct conformal field theory that describes each value of the angular momentum. In fact, those conformal field theories are definitely distinct. They have different central charges. So we have families of conformal field theories. In that setting, how would we describe a Rice-Northstone black hole? As in one that doesn't rotate. We will describe it as an average over theories. This is exactly how we do the precision countings of D1, D5 black holes, of ADS3 black holes, is that we consider a lot of CFTs. And in fact, we average over those CFTs just the way we average over states in a single CFT. Therefore, this procedure is what we actually do. You may not like it, but it's what we actually do when we do precision counting of entropy. It would correspond to saying that a non-rotating black hole actually is an average of all possible angular momenta. And the average is 0. But the corresponding microstate could easily be rotating one way, rotating another way, but since it's a mixed state that has all the different possible angular momenta, the average will look like it's a non-rotating black hole. Each sector of the rotation sector is, however, described by this very own theory. Therefore, actually, we have an ensemble of theories describing this situation, and that's a pretty standard situation for what we do in these more elaborate black holes. So this is a perspective on this apparent novelty of ensemble average. I believe we've been there before, we've accepted it, and didn't complain back then. So these are my final general comments. I just looked at the time. I did skip 3 slides in the middle there about quantum entropy, but I think I will simply let it go and just say that what I've done in this talk is given a few untraditional viewpoints. This is in many ways well-known material, but I have reworked it with my own perspectives, and I'm happy that at least some seems to get opposition, else it wouldn't be worth it. But this is how one tries to understand and refine our understanding of such things. My general research strategy is to do precision studies of more elaborate systems. For this purpose of this talk, I've just used this simple toy example, but in practice, we write similar formulas that have 6 parameters or whatever, and that means once you get agreements, you're pretty certain you at least got your algebra right. You might still not know, but what am I doing? But thanks for your attention. They're not part of the you're saying in the microcanonical, you're saying by definition, we specify the energy, is what you're saying.
I get to include a lot of states, but I don't get to include any states with the wrong energy just because I'm maybe going to compensate for that by also including.
No, that is correct. In a microcanonical example, you specify the energy, and the energy is therefore not thought about as an average over many states.
So now if I specify a black hole, like the kind that you consider, then I don't think I get to say that that defines an ensemble of states. It includes states that are inconsistent with the quantum numbers of that black hole.
In this case, it's not a state. In a higher dimension, it's a state. You can have a lot of states that correspond to different excitation along the horizon direction. But in 1+1D, suddenly you don't have horizon direction. So instead of the horizon excitation per Planck area, you have ensemble of theories with exactly the same energy. Now this is a space of microstates in a sense that you can take typical, generic,
Sorry, but we were not discussing theories on that slide. We were
so now it goes.
Duality with the ADS black hole, right?
Yes, I mean, because non-experiment case, it's just horizon. But in this case, it's the theory. So you have exactly the same energy, but with a different boundary theories corresponding to different
I
values.
wasn't asking about this. I was asking about something else. I was asking about the slide where we were discussing the duality between the collection of states of the CFT2 and a black hole involved. That one, yeah, that one. So I was objecting to including states with JL not equal to KL in the ensemble dual to the black hole, because that seemed analogous
not talking about the final conclusion, I think is right.
I can see what you're saying, but where I'm coming from has to do with what I introduced originally, is that I don't understand why we have this condition. Why is it that black holes only exist that satisfy two conditions? They have to satisfy the mass equal to whatever supersymmetry tells you, and in addition it had to do something else. It's like, why? The supersymmetry algebra did not obviously tell me that. It's something that's true for black holes. In fact, if the supersymmetry algebra had told me that there were two conditions, I wouldn't have found all these chiral primaries. Quite manifestly, the supersymmetry algebra is consistent with any JL. So the supersymmetry is not going to tell me why does this have to be the case. How come there are only black holes with this particular value? I'm saying I have an interpretation of that. There are actually possibilities that it could have been anything. Is not prohibited by supersymmetry, but by the laws of stat mech. You must, for large black holes, you must take the one that's the average. And because of here, we have a time reversal symmetry. Whatever the average really is, the one in the middle.
So this is kind of a speculation.
Well, it's an interpretation. It's an interpretation of a fact. The fact is that there's only one that does this. To me, this has been known for a long time in ADS3, but it's striking for me that we have now noticed it in higher dimensional ADSs. As I noticed and pointed out, now that you do mention it, we even knew that this was the case for, say, Kerr-Newman black holes. Now that you do mention it, rotation no good. You must have a different condition. That has been known for a long time, but I'm trying to put it in the context that there are, in other words, two conditions, m equal q and j equal to 0. Why is that extra j equal to 0? I'm interpreted as saying that actually there is nothing that the supersymmetry algebra that says that j should be 0 in our n equal 2 supergravity algebra. J does not have to be 0. We can have representations with any j that had m equal to q. However, we apparently only have black holes with j equal to 0. I'm interpreting that as saying that the microscopics of such black holes do have any j. However, because black holes do themselves very effectively average, they look like they have j equal to 0. That's an interpretation. You're correct.
Are you sure that if you take in strong coupling limit, all of these stays at the same dimension of the operators?
The dimension.
Different.
Well, obviously, by nature, that is exactly what I don't know, because you are right.
So
these things. No, but see, this is exactly the point. These states here, they can mix between one another. We expect when we turn on the coupling that they do mix. Chiral primaries are going to combine, they're going to separate, they're going to do crazy stuff. All the better. StatMech works much better when you have a coupling than when you have it free. StatMech doesn't work when it's a free system. You like it to have coupling. That's what makes it do extra well in taking averages. And this is why I feel that it is very reasonable that the black hole is an average.
But if that were the case, then this different value of j would appear as a black hole microstates in the bulk, because you can have an ensemble. But microstate is different theories. So this you view as one microstate from bulk point of view. So you have to dig up with everything else.
Each of these you're saying is, I didn't quite, this being what? Being this or that?
Because if this is an ensemble,
yes,
then you could at least say that the typical combination would be black hole. Because you cannot discriminate typical.
No. When I say ensemble, I agree that calling it typical state, yeah, I'm fine with that.
Then black hole entropy must come from the contribution from this from 0 to 2k.
Yes.
Oh, are you claiming this?
That certainly is part of where the entropy comes from.
So you don't need to do the ensemble of the theories.
I don't need to do. Well, in this case here, the way I've set it up, it's not, there is just one theory here on this slide. So there are other ways of setting it up. But here I do have a fixed central charge, and I'm looking at different sectors of a given theory. Yeah. So here it is true that I'm playing a little bit with words in this one here, but there are certainly other very closely related things where we do average over sectors with different distinct central charge, and we interpret that still as a single black hole.
Yeah, but that kind of thing, the
We think, not with precision.
But in external black hole, that is JT, black hole entropy corresponds to ensemble of theories. That's something people figure out.
Now you said JT and you said extremal. Come again? JT is for non-extremal. So it's near extremal and
then that black hole entropy corresponds to ensemble of boundary theories. At least in standard analysis.
are you talking about the ground state entropy now? Yeah. The ground state entropy comes from the ensemble of theories you were saying. I don't see it. I don't see how you can possibly justify that.
But you said that
No, but the ground state, but you brought up the JT story, and I'm saying that there just is no representation. There are not states enough. It's too small a theory to have states enough to account for the ground state entropy. It only is a theory of the excitations themselves. Right? Here I'm talking about theories where we actually have a theory of all the microstates. But in the standard discussion of JT gravity, that's just a theory of excitations above. It's the slow-moving excitations on the space of ground states. So we have a huge space of ground states, then slow motion on that space is what corresponds to what you're saying. That doesn't itself, when you're studying waves, you don't notice the ocean.
That's
right?
So it's here, right? But the black hole microstate is the wave of Dilaton in JT gravity. That's the part I was talking about.
Okay, but there are no states. You call it the waves of the dilaton, fine, that's a number, but that's not where are the states. What is it?
Oh, so that's why that represents that this entire system is an ensemble of theories. That's, I think, what we're usually talking about, this black hole entropy to be, ensemble of theories. Black hole. So maybe we're talking different things, but if that entropy is the case, then
I think I don't agree with that interpretation. Also, you actually had a question, so there, right? Yeah.
No,
okay.
I was just
back in the day. Okay. Just more questions?
Yeah.